March 12, 1918, Detroit, Michigan. The boardroom at General Electric's motor division would never officially record what their chief engineer said that morning about the massive horizontal stationary engine sitting in the demonstration hall downstairs. But the laughter echoed through 3 floors of the building. Through polished mahogany doors, executives gathered around technical drawings that showed an engine weighing 14 tons, a flywheel 8 feet in diameter, a crankshaft requiring 4 men to turn manually during startup, cooling systems that consumed 50 gallons of water hourly. Everything about the design seemed to belong in the previous century, not the modern industrial age. The competing technologies sat gleaming in the adjacent showroom. Electric motors, compact and efficient, requiring nothing more than a switch to deliver instant power. No coal, no water, no maintenance crews, no specialized operators. General Electric's latest designs could replace 5 steam engines with a single motor 1/10 the size and 1/20th the weight. European factories had already begun wholesale conversions to electric power during the war years. British manufacturers reported production increases of 40% after abandoning internal combustion entirely. German engineering journals published calculations proving that stationary engines would become industrial museum pieces within 5 years. French factory owners who still operated combustion power plants faced ridicule from competitors who had modernized. American industrial consultants issued unanimous recommendations. The Edison Illuminating Company projected that electric motors would power 95% of American manufacturing by 1925. Investment analysts advised against purchasing any equipment that relied on combustion engines, warning that replacement parts would become unavailable as manufacturers discontinued obsolete product lines. The Worthington Machine Company had bet their reputation on the horizontal stationary engine despite universal skepticism from engineering authorities. Founded in 1845, the company had built water pumps for New York City, steam engines for Mississippi riverboats, and hydraulic equipment for the Panama Canal. Their engineers understood industrial power requirements through decades of solving problems that textbook theories couldn't address. Henry Worthington, grandson of the founder, had personally supervised development of the Model H Series horizontal engine. At 62 years old, he had witnessed every major power technology transition since the Civil War. He had watched steam give way to internal combustion, seen hydraulic systems replace mechanical linkages, observed electric motors transform factory design. But Worthington recognized something the efficiency experts missed. Industrial production didn't just require power, it demanded constant, reliable, unstoppable torque under conditions that would destroy delicate equipment. The massive flywheel that seemed wasteful to efficiency analysts actually stored kinetic energy that smoothed power delivery through load variations. The oversized crankshaft that appeared outdated provided strength margins that prevented catastrophic failure during peak demand cycles. The decision point arrived when Bethlehem Steel Corporation announced plans to expand their foundry operations in Pennsylvania. They needed power systems capable of driving rolling mills that shaped 16-inch steel beams, equipment that could operate continuously for weeks without shutdown, reliability that couldn't accept the brownouts and voltage fluctuations affecting early electric grids. General Electric submitted a proposal featuring their newest 3-phase motors. Westinghouse offered competing designs with superior efficiency ratings. Both companies promised delivery within 6 months and guaranteed performance specifications that exceeded Bethlehem's requirements on paper. Worthington proposed something different. An engine nobody wanted, using technology everyone had rejected, requiring infrastructure that seemed impossibly complex compared to simply plugging into electrical service. The contract negotiation would determine whether American industry's future belonged to compact efficiency or unstoppable permanence. Bethlehem Steel's chief mechanical engineer, Thomas Waverly, understood the stakes involved in choosing Worthington's horizontal engine over General Electric's modern motors. His career depended on making decisions that kept the foundry running 24 hours daily without interruption. Production delays cost thousands of dollars hourly when rolling mills sat idle, waiting for power restoration. Waverly had spent 3 months studying electric motor installations at competing steel plants throughout Pennsylvania and Ohio. What he observed contradicted the optimistic projections from equipment manufacturers. Republic Steel's Cleveland facility experienced 17 power interruptions during his site visit. Jones and Laughlin's Pittsburgh operation maintained backup steam systems after electric motors failed during a thunderstorm that knocked out grid power for 6 hours. The technical reports from European factories revealed problems buried beneath efficiency statistics. British plants reported that electric motors delivered consistent power only when grid voltage remained stable. Fluctuations of more than 5% caused motors to overheat or stall completely. German manufacturers discovered that the weight savings from eliminating flywheels created vibration problems that cracked equipment foundations and loosened machinery mounting bolts. Worthington's Model H18 horizontal engine operated on principles that predated electric power entirely. The massive cylinder contained a piston 18 inches in diameter driven by controlled explosions of coal gas mixed with atmospheric air. Each power stroke turned the 8-foot flywheel, converting explosive force into smooth rotational energy through sheer mechanical momentum. The fuel system burned low-grade coal gas that steel foundries produced as a waste byproduct during coke manufacturing. Plants that installed electric motors had to pay for grid electricity while simultaneously disposing of coal gas they couldn't use. Worthington's engine converted that waste into productive power, essentially operating without fuel costs beyond the coal Bethlehem already purchased for steelmaking. Starting procedures required methodology that seemed antiquated compared to flipping a switch. Operators manually rotated the flywheel to position the piston properly, opened fuel valves, adjusted ignition timing, then engaged a manual starting crank that required sustained effort from 2 strong men. The entire startup sequence took 15 minutes compared to the instantaneous power delivery from electric motors. But once running, the horizontal engine exhibited characteristics that electric motors couldn't match. The 14-ton flywheel stored enough kinetic energy to maintain constant speed through load variations that would stall smaller equipment. When rolling mills grabbed 16-inch steel beams and began compressing them under tremendous force, the engine's speed decreased by less than 2%. Electric motors under identical loading conditions experienced speed reductions exceeding 20%, creating quality problems in the finished steel. Cooling requirements seemed excessive until engineers examined the heat management advantages. 50 gallons per hour of circulating water removed waste heat before it could damage internal components. The cooling jacket maintained cylinder temperatures within optimal ranges regardless of ambient conditions or loading patterns. Electric motors relied on air cooling that became inadequate during summer heat or when equipment operated above rated capacity. Waverly's decision came down to a fundamental question about industrial philosophy. Would Bethlehem Steel optimize for the theoretical efficiency that engineers calculated in comfortable offices, or the practical reliability that kept production running when equipment faced real-world conditions that nobody could predict completely? The contract signature would commit Bethlehem to technology that every expert had declared obsolete, using an engine that weighed as much as 10 modern motors combined. August 1918 brought the Worthington Model H18 to Bethlehem Steel's foundry on 20 railroad flat cars. The locomotive that pulled them struggled with grades that normally presented no difficulty, testimony to the density of cast iron and forged steel. Comprising the engine's major components, riggers using steam cranes spent 11 days positioning the base casting onto foundations that extended 14 feet below ground level. The foundation work had begun 3 months earlier after soil engineers discovered that Bethlehem's existing concrete slabs couldn't support concentrated loads exceeding 8 tons per square foot. The horizontal engine's weight distribution required excavating clay until they reached bedrock, then building up layers of reinforced concrete designed to absorb vibration frequencies that would crack standard industrial flooring. Assembly proceeded through methods that seemed primitive compared to the modular installation of electric motors. The crankshaft alone required a specialized crane capable of lifting 6 tons with precision sufficient to align bearing surfaces within tolerances measured in thousandths of inches. The connecting rod, forged from a single piece of chrome nickel steel, weighed 1,100 pounds and demanded careful heating before installation to ensure proper fit as components cooled to ambient temperature. Worthington's installation supervisor, Jakob Steinmann, had emigrated from Germany in 1905 after apprenticing with MAN Diesel in Augsburg. He understood that the engine's reliability depended entirely on precision during assembly. Each bearing received individual attention as Steinmann verified contact patterns using Prussian blue transfer compound. Any high spots or binding points got hand-scraped until bearing surfaces exhibited the uniform contact distribution that would prevent premature wear. The fuel system installation revealed engineering sophistication hidden within the engine's apparently simple design. Coal gas from Bethlehem's coke ovens contained impurities that could damage components over time. Steinmann supervised installation of filtration and scrubbing equipment that removed sulfur compounds, tar particles, and water vapor before fuel entered the mixing chamber, where precise ratios of gas and air created the combustible mixture driving the piston. Governor systems controlled engine speed through centrifugal mechanisms that adjusted fuel flow automatically in response to load changes. When the rolling mill grabbed steel and increased power demand, the flywheel's rotational speed decreased slightly. Weighted arms in the governor assembly dropped inward, opening fuel valves further to maintain programmed operating speed. The entirely mechanical system required no electric controls, no external power sources, no electronic components that could fail during voltage fluctuations. September 28, 1918, marked the first startup attempt. Steinmann personally verified that cooling water flowed properly through jacket passages. He checked oil levels in the sight glasses monitoring lubrication delivery to each bearing surface. The fuel valves opened smoothly when tested manually. Ignition timing mechanisms operated with the precise coordination that separated successful engines from expensive scrap metal. 4 foundry workers positioned themselves around the manual starting crank while Steinmann adjusted fuel mixture controls. The flywheel required 3 complete rotations before compression built sufficiently to ignite fuel. On the 4th revolution, the engine fired with a deep concussion that rattled windows throughout the foundry building. Exhaust gases roared from the stack as the flywheel accelerated toward operating speed. Steinmann monitored pressure gauges, temperature indicators, and vibration levels as the engine stabilized at 120 revolutions per minute. After 5 minutes of warm-up, he engaged the belt drive connecting to the rolling mill's main shaft. Bethlehem Steel's newest power plant had officially entered service, ready to prove whether obsolete technology could outperform modern alternatives. October through December 1918 generated operating data that contradicted every prediction from electric motor proponents. Bethlehem Steel's rolling mill processed 4,000 tons of structural steel beams during that period, working 3 8-hour shifts daily without the engine missing a single hour of scheduled operation. Chief Engineer Thomas Waverly documented performance characteristics that revealed why theoretical efficiency calculations had missed crucial practical advantages. The rolling mill's work cycle created power demands that varied dramatically within seconds. When hydraulic rams grabbed cold steel billets and forced them through compression dies, instantaneous power requirements jumped from steady-state levels to peak loads exceeding twice the engine's continuous rating. Electric motors at competing foundries experienced voltage drops and speed reductions that created quality problems in the finished beams. Dimensional tolerances suffered when mill speed fluctuated during the compression cycle. Worthington's massive flywheel transformed these violent load changes into minor speed variations. The 8-foot diameter wheel spinning at 120 RPM stored kinetic energy equivalent to 1,100 horsepower seconds. When rolling forces spiked, the flywheel surrendered stored energy while the engine gradually increased fuel flow to restore rotational speed. By the time each billet passed through the dies, engine speed had returned to normal without the dramatic fluctuations affecting motor-driven equipment. Temperature stability provided another unexpected advantage. Electric motors operated efficiently only within narrow temperature ranges. Summer heat caused insulation degradation and bearing failures that shut down production at the worst possible times. Winter cold increased starting torque requirements and created condensation problems in motor windings. Bethlehem's foundry operated in an environment where ambient temperatures ranged from 30 degrees Fahrenheit in January to 110 degrees near the furnaces in July. The horizontal engine's water cooling system isolated internal components from environmental temperature extremes. Cylinder walls maintained optimal operating temperature year-round through controlled water circulation. The cooling jacket removed waste heat so effectively that external surface temperatures never exceeded levels comfortable for human touch. This thermal management capability meant consistent performance regardless of whether Pennsylvania weather brought blizzards or heat waves. Fuel costs created the most dramatic economic advantage. Bethlehem Steel produced coal gas as an unavoidable byproduct of metallurgical coke manufacturing. Before installing the Worthington engine, they flared off approximately 8 million cubic feet monthly, converting valuable fuel into waste heat that contributed nothing to production. The horizontal engine consumed 600 cubic feet per hour when operating under full load, transforming waste gas into productive mechanical power. Competing foundries operating electric motors paid utility companies for grid electricity while simultaneously burning off their own coal gas because they had no way to use it. Bethlehem's fuel costs for the engine consisted entirely of the coal they already purchased for steelmaking. Accountants calculated that the zero-cost fuel advantage saved $2,200 monthly compared to purchasing equivalent electricity from Pennsylvania Power and Light. Maintenance requirements defied predictions from engineers who claimed internal combustion engines demanded constant attention. The first 3 months of operation required only routine lubrication and periodic valve adjustments. Steinman's crew checked bearing temperatures daily, topped off cooling water weekly, and adjusted governor settings when seasonal temperature changes affected fuel density. Total maintenance labor averaged 4 hours weekly, substantially less than the attention required by steam engines of comparable output. By December 1918, Waverly's gamble had transformed into vindication. The engine nobody wanted had become Bethlehem Steel's most reliable power source. Spring 1919 brought fundamental shifts in American industrial attitudes toward horizontal stationary engines as word spread through manufacturing networks about Bethlehem Steel's operational results. The skepticism that had greeted Worthington's designs gave way to serious inquiries from foundries, textile mills, and factories facing reliability problems with electric motor installations. Republic Steel's superintendent visited Bethlehem in March after experiencing their 14th motor failure in 6 months. He watched the Worthington engine drive the rolling mill through a complete production shift, noting the absence of speed fluctuations that plagued his Cleveland operation. Within 2 weeks, Republic ordered 3 Model H-18 engines for immediate installation. The conversion from electric motors to combustion power reversed the technology transition everyone had predicted was inevitable. Textile mills throughout New England discovered that constant speed operation mattered more than efficiency percentages when producing thread and fabric. Electric motors subject to grid voltage variations created tension inconsistencies that resulted in defective products. Mills operating near capacity couldn't absorb the waste from substandard output caused by power fluctuations beyond their control. The Lowell Manufacturing Company in Massachusetts became the first textile operation to install a Worthington horizontal engine in June 1919. Their application required driving spinning frames containing 12,000 individual spindles, all of which needed perfectly synchronized rotation to produce uniform thread. The engine's flywheel provided the mechanical stability that prevented the tension variations causing quality problems. Lumber mills in the Pacific Northwest faced different challenges that horizontal engines solved better than any alternative. Sawmill work involved intermittent heavy loading as circular blades cut through logs that varied dramatically in size and density. When blades encountered knots or shifted from softwood to hardwood, power demands spiked instantaneously. Electric motors stalled regularly under these conditions, requiring time-consuming restarts that reduced productivity. The Weyerhaeuser Timber Company installed their first Worthington engine at their Longview, Washington facility in August 1919. The Model H-24 featured a 24-inch cylinder that developed 600 horsepower at 100 RPM. The mill superintendent reported that the engine's massive flywheel stored enough energy to cut through Douglas fir logs 4 feet in diameter without noticeable speed reduction. Within 18 months, Weyerhaeuser had converted 17 sawmills to horizontal engine power, abandoning electric motors entirely at locations where grid reliability proved inadequate. Municipal water systems created markets that engine manufacturers hadn't anticipated. Cities installing modern water treatment and distribution systems needed pumping equipment capable of operating continuously without supervision. Electric motors required constant monitoring for overheating, bearing failure, and insulation breakdown. Extended power outages meant water supply interruptions that created public health emergencies. The city of Indianapolis installed a Worthington Model H30 at their main pumping station in October 1919. The engine drove centrifugal pumps that supplied water to 80,000 residents. City engineers specified the horizontal engine specifically because it could operate unattended overnight and through weekends without reliability concerns. The installation included automatic governor controls that maintained water pressure within designed parameters, regardless of demand fluctuations as residents used water throughout daily cycles. By December 1919, Worthington's production capacity couldn't meet demand. The company broke ground on a second manufacturing facility in Pennsylvania, tripling their ability to produce horizontal engines. The backlog of orders extended 14 months into the future as American industry discovered that the technology experts had declared obsolete was actually solving problems that modern alternatives couldn't address. The 1920s established horizontal stationary engines as the backbone of American industrial expansion during the decade when manufacturing output more than doubled. Worthington and competing manufacturers including Fairbanks Morse, De La Verne, and Nordberg produced thousands of engines ranging from 50 to 3,000 horsepower as factories, mills, and municipalities discovered that reliability mattered more than theoretical efficiency. The economic boom created demand for products that required manufacturing processes beyond the capabilities of grid-dependent electric motors. Steel mills expanded production to build skyscrapers transforming city skylines. Automobile factories needed power systems supporting assembly lines that couldn't tolerate interruptions. Cement plants processing limestone into construction materials operated in remote locations where electric service remained unavailable. By 1925, more than 18,000 horizontal stationary engines powered American industry. The installed base represented approximately 30% of total industrial power capacity, a market share that would have seemed impossible in 1918 when experts predicted the technology's imminent extinction. Engineering journals that had ridiculed combustion engines now published technical articles analyzing the operating characteristics that made them indispensable for demanding applications. The Great Depression paradoxically strengthened horizontal engines' market position. When banks failed and construction stopped, factories operating electric motors faced difficult choices about paying utility bills while production declined. Plants with horizontal engines continued operating on coal gas from their own industrial processes, essentially powering production without cash expenditures for fuel. The economic advantage of converting waste products into productive power became critical during years when every dollar mattered. World War II transformed horizontal engines from industrial workhorses into strategic assets supporting military production. Shipyards building, Liberty ships, and aircraft carriers needed power systems immune to sabotage and enemy action. Defense planners recognized that factories dependent on electric grids represented vulnerabilities that enemies could exploit through infrastructure attacks. Plants operating self-sufficient combustion engines could continue production even if grid power failed. The Bethlehem steel engine installed in 1918 worked continuously throughout the war, supporting production of armor plate and structural steel for naval construction. The foundry operated 3 shifts daily, 7 days weekly for 4 years, without the engine experiencing downtime for anything beyond routine maintenance. Engineers calculated that the original installation had accumulated 84,000 operating hours by 1945, equivalent to running nonstop for nearly 10 years. Post-war industrial surveys documented the remarkable longevity of engines manufacturers had claimed were obsolete decades earlier. The average horizontal stationary engine installation exceeded 25 years of continuous service before requiring major overhaul. Many units operated 40 years with nothing more than bearing replacement and periodic valve work. The durability advantage over electric motors became undeniable when motors typically needed replacement after 15 years of service. The Lowell Textile Mill's Worthington engine celebrated its 25th anniversary in 1944, having driven spinning frames through the entire interwar period without missing a scheduled production shift. Republic Steel's original 3 engines acquired in 1919 remained in daily operation through 1950, outlasting 3 generations of electric motors at competing foundries. Municipal water systems discovered that horizontal engines often outlived the pumps they powered, requiring pump rebuilds while engines continued operating with original components. The technology dismissed as antiquated had proven itself through the most demanding test possible. Decades of relentless service under conditions that destroyed supposedly superior alternatives. The transition to universal electric power during the 1950s and 1960s finally accomplished what efficiency experts had predicted in 1918, but the timing revealed how badly early projections had underestimated horizontal engines' practical advantages. It took 40 years of grid expansion, voltage regulation improvements, and backup power system development before electric motors could match the reliability that combustion engines had delivered from their first day of operation. The Bethlehem Steel Foundry finally retired their original Worthington Model H-18 in 1967 after 49 years of continuous service. The engine had operated approximately 120,000 hours, equivalent to running non-stop for nearly 14 years. Final inspection revealed cylinder walls showing minimal wear, bearings within original clearance specifications, and the massive crankshaft exhibiting no detectable fatigue cracks despite millions of stress cycles. Engineering analysis comparing the horizontal engine's total cost of ownership against electric motor alternatives produced calculations that vindicated Thomas Waverley's 1918 decision. The engine's initial purchase price had exceeded comparable motors by 60%, but maintenance costs over 49 years totaled less than $15,000, while motor-equipped foundries replaced equipment multiple times at costs exceeding the original engine investment by substantial margins. Fuel costs remained effectively zero throughout the engine's service life as Bethlehem Steel continued producing coal gas from metallurgical coke. The avoided electricity expenses, calculated at average industrial rates over 5 decades, exceeded $280,000. The economic advantage of converting waste products into productive power had proven more valuable than anyone imagined when critics dismissed the technology as inefficient. Museums and industrial historians now preserve horizontal stationary engines as monuments to an era when American manufacturing valued permanence over planned obsolescence. The Henry Ford Museum in Dearborn, Michigan displays a fully restored Worthington Model H-18 that visitors can observe operating under compressed air power. The Smithsonian Institution includes a sectioned de la Vergne engine in their Industrial Technology Collection, allowing visitors to examine internal components that operated reliably for decades. Private collectors maintain dozens of operational engines, demonstrating mechanical principles that younger engineers have never witnessed. The massive flywheels spinning at stately speeds provide visceral understanding of momentum and energy storage that computer simulations cannot replicate. The deep, rhythmic exhaust note creates sensory experiences, connecting modern observers to industrial heritage spanning a century. Contemporary manufacturing faces renewed interest in on-site power generation as grid reliability concerns return. Solar installations and battery storage represent modern approaches to the self-sufficiency that horizontal engines provided through fuel conversion. The fundamental principle remains unchanged. Industrial operations requiring uninterrupted power cannot depend entirely on external suppliers whose reliability they cannot control. The engine designers rejected in 1918 because it seemed too large, too inefficient, too outdated ultimately powered American industry through its greatest expansion period. Those massive flywheels, oversized cylinders, and elaborate cooling systems solved real problems that theoretical efficiency calculations missed completely. The technology survived 4 decades, not because engineers were wrong about electric power's advantages, but because reliability and fuel flexibility mattered more than efficiency percentages in industrial applications, where downtime meant complete production failure. The horizontal stationary engine's legacy endures as testament to engineering decisions valuing practical performance over fashionable efficiency, long-term durability over initial cost savings, and proven reliability over theoretical superiority.